So yesterday we looked into a representation, term document indices matrix. Our goal here is to find out appropriate documents related to a query string. What is a query string? I want a document, I want a newspaper that contains Gandhi, Mandela, and no, but not Luther King. That's a query string. I need to find out the documents which are having this kind of data. Google is doing that. You type a query string, right? Maybe you type a query string like this. Oh, I got it into this. You type a query string like Java. So that's a query string, right? Java bike showrooms near me. Right? That's a query string. It actually pulled out all the related stuff. If you go right, it actually pulled out maybe 10 pages of documents, or even maybe 100 pages of results. Do you think all results are going to be exactly matching the Java bike showroom? Do you think?
It can be independent word match also.
Yeah, but for this particular query string, do you think if I traverse through maybe 10 100 documents, right? Next 10, like that I am traversing. Do you think this last page also talks about the showroom? Do you see this one? Is it talking about showroom? It is just talking about the Java bike. That's it, right? So similarity, right? We are actually trying to find the similarity between the query and the documents and trying to pull out. There may be exact match, or there may be a little match also. But if you take the Boolean retrieval model or the term document matrix, it will actually get exact match or no match. Google is not definitely not using this. Okay. So exact match or not match. How can we find? That's the problem we are trying to solve. First, we took this representation, term documents indices matrix. It's going to occupy too much space, right? The example is like if you have 500,000 distinct words in 1 million documents, it's going to occupy 500 GB of space, and it is all sparse. We don't know whether we do a query, we'll get whether one result or 0 results or maybe 10 results, right? If you spend this much of space, at least you should get some similar document. Even if the exact match is not there, you should get some similar document. So to solve this space problem, we took inverted index approach. Inverted index will take the terms, and then the documents which have the term present. Term present in the sense Gandhi ji may be present, Mohandas Karamchand Gandhi may be present, Rahul Gandhi may be present, Indira Gandhi may be present, right? Gandhi is the term, right? The tokens may have, right? I actually took a wrong example, but run, running, ran, right? These three are three different tokens, and run is the term, right? We are going to take all terms as a dictionary, and we'll have a mapping between the terms and the newspaper list. But here we are solving only the memory issue. The amount of memory it is occupying, we are solving that. But uh, whether the query, whatever we typed, in the order in which we typed, is it present in the document or not? We are not sure, because the positional indexing is not there. Only inverted index it is. To solve that, we have taken positional, the positional indexing. It's somewhere here. Positional indexing. Positional indexing actually tries to track where exactly the particular term occurred. This way you will know Gandhi met Mandela, right? Gandhi met and or Luther met Gandhi, right? That's actually right. Maybe newspaper 2, newspaper 3, both. No, there is no match, right? Luther and Gandhi, they are not present in the same document. If they are present, we will know which one occurred first, which one occurred next, and how many, how many terms are in between. Also, we know, right? Newspaper 2 has got Luther and Gandhi both. Luther occurred first, Gandhi occurred third. That means the second word may be met. So most probable match we will find, right? So positional indexing is solving the, you know, the count problem, right? How many times a particular term occurred, and whether the order in which the query was typed is also being solved. I have taken skip pointer list to show you that searching, sorting algorithms are also important to build information retrieval systems. Whether it is a image search or a document search, a data scientist should have a little bit of understanding of this searching and sorting algorithms also. Okay, we may have to, right? That's not, it is very rare. It is very rare, but I'm just trying to show you the scope of whatever, right? And then there may be phrase queries, right? Phrase queries means we were actually trying to look at Stanford University in our
Sir, one
initial
second,
class.
sir.
Sorry?
Sir, 1 second before go here. So in the positional one,
Yeah.
so even it actually takes a lot of memory, right?
Yeah, a little more than inverted index, but not lot.
No, the first one we said like it is actually not counting the number of occurrences. It only identifies whether a particular word is there in the document or not.
Yes, sir.
There we have actually calculated yesterday, like if there are 2 million records or so, right? But here in the positional index, so for a single word,
Too
it
many
is actually,
records?
yeah, for a single word, in the first example, in the first method, for a single word, there is only one with one bit, whether 0 or 1.
One, yes.
But here it is sorry. If a single word is repeated many times and it's actually capturing its position, many positions.
Yeah.
So it is far bigger. It requires far bigger memory than the first approach.
There it is a matrix. It is right. This is a matrix, right?
Yeah. Yes.
But here it is a list, dictionary.
Okay.
Dictionary, dictionary with a list of lists. A dictionary with key Gandhi, and this is a list, right? Luther, take Luther, right? Luther is a key, and this is a list, and each list has got another list, right? Maybe a dictionary again, maybe dictionary and a dictionary with list, and we are actually having a list of dictionaries here. Got it?
Sir, can I just add one elaboration point, sir?
Yeah.
Shishram Garu, if you consider, let's say, the number of documents equal to 1 lakh documents, just assume, okay? And the word is present only in 2 documents. Now, if you take the first first one, Lakshman, then I think you can visualize how it is making difference.
Right.
It is only capturing the occurrences. There it is yes or no, both are there. Zeros are also there, right?
In the first representation, right, you'll have 1 lakh cells.
Yeah.
Even though it is occurring 2 times, you will have 1 lakh cells, and only 2 places you will have 1.
Yeah,
but here,
there it is not occurring is also captured. Here only occurring with the position is captured. Yeah.
Yes.
Yeah, Girigar, that's right.
Yeah, that's a good example, and good. I can see a good teacher in Girigar. I don't know. Do you have any experience with teaching, sir?
No.
Okay. Yeah. Whenever I show something, right, you actually try to see gap, in that space, and the explanation also is good. Good, sir. Thank you.
Yeah, I'm just trying to elaborate, sir.
Yeah.
I'm not contradicting with what you are saying. I'm just trying
No. Contradiction is also fine, right? Discussion should happen. Listening and discussing is good. If somebody is not listening and running away, right? That's not good. Whether we know or don't know, that nobody can know everything. That's the truth. So we should base on that and talk, right? If I don't know, I don't know. I know. That's Yeah. So you got the clarity, right? Shishram.
Yes, sir, that's right.
Now the phrase queries, right? Here we were actually looking at only one word, right? In a word we have only one token, right? One what you say, one word, right? So if you have multiple words in a query, and it is called as a phrase queries, right? Stanford University is a phrase query. It is not that we are looking for Stanford separately, university separately. We are looking for Stanford University as a whole. So if you have to find Stanford University, byword index is another approach, right? You can take the positional index or normal inverted index. Right? If you take positional indexing, it is better. But if you take, for example, I have taken inverted index here, right? Byword index is going to have Stanford University. University is a private, right? If you see the document, Stanford University is a private research university in Stanford, California, right? Stanford is known for its academic strength, weakness, and whatever. This whole document is talking about some Stanford University. And when I am creating the inverted index or positional index, I'll be taking two words at a time. Stanford University, university is this is byword index, or bigram index, right? We were actually looking at unigram, bigram, trigram, right? So bigram index we can say it as, or byword index, right? If the two words are occurring in a document, right? Two words are occurring in a document, you can actually, this actually shows that newspaper 2 has got that, right? So this also has got some problem, right? How to use byword indexes for long phrase queries? Find positions, postings list for all byword phrases, and apply end operation to get final result of the document. But if you have Stanford University Palo Alto, okay, this will be handled like Stanford University. There is some document, right? And then where exactly it occurred, and University Polo, where exactly it occurred, right? University Polo is another term, where exactly in which document it occurred, and then Polo Alto, where exactly in which document it occurred. In the positional indexing you can take, and then depending on the positions you can actually exactly find out whether it is whether this whole string is present or not. Stanford University Palo Alto is present or not. But right, see, in this inverted index, right, you cannot find out whether it is exactly next to each other or not. But if you take positional indexing, right, you can definitely find it out. So positional indexing is better compared to inverted index also. Even if it is byword, byword index, it is always better to take a positional indexing. Right? This is one of the best approaches to find out this phrase queries in a most efficient way. But we have even better approaches. If in this also we may not get. Sometimes it is like. Uh, in positional indexing, if you are looking for this particular sentence, right, Stanford University Palo Alto, if these phrases did not occur next to each other, you will not get anything, you will not get any result there, right? You can actually write code in a way that even if it matches a little bit, you can get it, right? Not like completely like what you call it as Boolean retrieval model, but still it is a tedious process. Okay, we have even better approaches. I'll talk about them in a moment. Problem with above long phrase queries is that there may be documents containing only Stanford University, only University Polo, only Palo Alto, right? So if you have this positional indexing, right, that only thing can be solved. We can know that whether they are occurring next to each other or not by looking at the index, and then find out. So extending byword index, most of the user queries in search engines will contain nouns. NLP technique, POS tagging on documents will make words with appropriate tags. Give me 1 second. Sorry, somebody came. Okay. So most of the user queries in search engines will contain nouns. NLP POS tagging and documents will make words with appropriate tags. Now we can create byword indexes with nouns in documents. Right? So instead of taking all the tokens and trying to all the terms and trying to create the byword index or positional indexing, if you create the positional indexing with nouns only, that reduces the size, and that may actually find out the results, more results basically. That when you actually type some query in Google, it is not exactly matching. It is just not exactly matching. It is actually trying to find out near to whatever query string is, right? So that kind of results you can produce. Okay, so these are different representations, right? We have more sophisticated ways of finding our information retrieval. Okay, so I'm actually thinking here. Yeah, rank retrieval model. The next model. So there is some theory here. I'll talk about it on Monday, but I'm actually talking about rank retrieval model. So here we looked into Boolean retrieval model and index-based retrieval models. Now we are going to talk about rank retrieval model. There are other approaches there, for spelling corrections and all. I'll talk about them later, okay, because these are connected. Okay, rank retrieval model assigns rank to each document. So in the previous approach, right, we're actually trying to see whether a document has got a particular string, particular term, or a phrase. Based on that, we are actually trying to estimate whether the query matches the document or not. Right? It is like if you have a million tokens, you need to actually go through all the documents which are related to those and then need to bring out. Instead of doing that, based on the query, we can assign some rank to document. Okay. If I type, Java bike showrooms near me, I'll take that query and I'll have already documents in the database and try to assign documents a rank based on this query. If I type a new query, right? Now, how is the kick movie? Right? That's a new query. Based on that query, I am going to assign rank to the documents again. Based on that rank, I am going to sort it and show the results. That's how the Google search is actually working. Okay, rank retrieval model assigns a rank to each document. The rank is a real number between 0 and 1. Right, best match is 1. It is probability. 0 and 1. Rank retrieval model accepts free text queries rather than queries with operations and expressions. Right, in the Boolean retrieval model, you need to specify and, or, like a developer you need to write. Okay, so in the rank retrieval model, there are two approaches. One is Jaccard coefficient. Another is weighted term frequency and bag of words model. Okay, so we have seen the bag of words model, but weighted term frequency we'll see today. Right? What is Jaccard coefficient? We need to understand. Based on Jaccard coefficient, we can assign rank. Now this approach looks at n-gram overlap. Okay, there are a couple issues with the Jaccard coefficient. We'll see issues later, but first we'll see what is Jaccard coefficient. I said this approach looks at n-gram overlap, right? N-gram overlap means what? See, this is Jaccard coefficient. So n-gram overlap also they call it as. And in scikit-learn and other packages, right? We have NLTK, scikit-learn and other packages. We have method to calculate this score, Jaccard coefficient score. So how will it work? I have important and mutant, right? Two terms. I wanted to see how close they are. Okay, so suppose that we are trying to do spelling correction. If I say I am PARTANT and I am PORTANT, right? Important, right? So I am PARTANT, right? It's a mistake, right? It's a spelling mistake. See, it actually pulled out important. How did it pull out? It actually has calculated a Jaccard coefficient between this term and all the terms which are present in the dictionary. Maybe the term starting with I, maybe the term starting with IM, maybe the word starting with IMP. It actually took all those words and calculated Jaccard coefficient. What is Jaccard coefficient? See, important and mutant I have taken. I have taken trigrams of IMP. See this IMP, MPO, POR, ORT, right? RTA, right? TAN, ANT, right? I splitted this whole thing into trigrams of characters, and mutant also I splitted, and then I am actually trying to see any overlap between these two. N-gram overlap, trigram overlap it is. You can take 4 grams, you can take 2 grams, right? Unigram also you can take, right? So is there any overlap between these two? Unigram means each character. Okay, so any overlap between, if you take important and important, right, will you have anything in this space and this space? If you take important, will you have anything here, or you will have everything here? Two words are same, then the intersection is going to have all those trigrams, right? Do you agree? Do you agree?
Yes, sir. Yes.
Yeah. If I take important and Joe Biden, right, nothing will match, right? None of the trigrams will be present in the intersection. So you will calculate intersection or union. If intersection is having all the values and union will also have all the values, you will get one. Important and important, you are trying to see similarity, then you will have one. Important with a spelling mistake like A in between, like this A and O are not matching, then maybe around 3 to 4 trigrams will fall here and there, and most of them will be in the intersection, so you will get more score. So whichever is actually matching, right? So if for important, whichever is having highest score, intersection or union you call it as. The same technique is used in computer vision also. Okay, we'll talk about that when we talk about YOLO algorithm. The same technique we use it. There they call it as intersection or union. Here we call it as Jaccard coefficient or n-gram overlap. Okay, same thing, same formula, same concept, but names are different. N-gram overlap, Jaccard coefficient, intersection or union are all same. Okay, so here if you look at that, right, so if none of them are matching, you will get 0. Intersection will be 0 and union is going to be complete total, total unigrams, the total trigrams, right? So like that. So 1 means close to 1 means best match, 0 means no match, right? The n-gram overlap between query string and lexicon, the dictionary word, is less than length of query. The lexicon matches a little bit, right? So I think whatever we have seen here is good enough. I tried to put it into textbook kind of a thing here. Right? Lexicon means what? Lexicon means the syntactical words. Syntax is also known as lexicon, right? So syntactic words which are present in dictionary, right? So n-gram overlap between the query string. Important, IMPARTANT is the query string, right? Lexicon present in the dictionary is IMPORTANT, right? Is equal to length of the query. That means the same thing. Query string without the spelling mistakes will get you the length of the query. right? If the completely different thing, you typed ABCD in the query, and in the dictionary you will not have ABCD, so you will get 0. So there is no match, right? If it is like, a little bit of match is there, then it's going to be a little less than whatever, right? Lexicon of whatever is less than lexicon of query, right? That kind of thing. So I think you got it, right? What is the n-gram overlap?
Sir, one question, sir. So
Yeah.
here in the formula, what are you mentioned here? X is nothing but our query string, and Y is the dictionary word. Is that what?
Yes, sir. Yes, you can take either way, right? Yeah.
Example, as an example, X
Yes.
is the query string, and Y is the dictionary word.
Yes, sir. Yes, and Y will be many, right? Y will have many words. X will have, whatever you type, you query string, whatever. Here I took only one word, but you can take multiple words also.
Yeah.
For spelling correction, Jaccard coefficient is, useful, more useful, rather than for the actual query match. Yeah.
Sir, one question, sir.
Yeah.
So when we are actually doing the count vectorizer, we said n-gram, right? So there actually it is applying on the words. So here it is applying on the words, and at the same time, we said a column can be formed with single word and words besides
Yes, sir.
this continuous words, two continuous words if it is bigram.
Yeah.
So here it looks like there are two different.
Yeah, we are actually taking the word and trying to split it into, trigram or, yeah.
And if we are saying here trigram, it is only splitting the one word based on the characters into a word with 3 characters. We are not we are. I mean, it is not splitting a single character, 2 characters, and 3 characters.
Yeah, that is true. But yeah, that's true, right? Yeah, in the concept is same, yeah, but not exactly same. But that's concept is similar, right? Here and there.
Yeah, concept is similar.
But here, granular level, gramming is needed, right? If you don't do granular level, right, character level, the trigrams split, right, you will not get. If you have a person running on road, a person running on roads, right? Right. So that if you don't do this way, it is not going to give you more appropriate probability. Yeah, that is true, right? There we are not actually doing character level split. It is word level n-grams. These are character level n-grams. Correct, yeah. Statement, the similar things they're not saying.
Yes, sir. So if we ask the particular algorithm or whatever the method, here it applies like split based on the character. There is it applies based on the words.
Words, yes, sir. Word level, word n-gram and character n-gram.
Okay, sir.
So Jaccard coefficient given a normalized gives a normalized score between query string and lexicon n-gram. We can set threshold 0.6 coefficient to choose the best matches. That's okay. That's the. So using this, you can actually find out best query documents also. Right? I typed, Java bike showrooms near me, right? So you have million documents or billion documents, and Google has got billion documents in their database, and immediately it will actually try to see the nouns in the text and see, it would have built it would have indexed the data based on nouns or maybe other ways also. But as an example, I am trying to say that based on nouns it will build indexes. When I say index, out of billion documents, it will take the documents which are related to Java and put it into one block, or maybe In another database table, it will try to put the indexes of those records wherever the documents are present, right? As soon as it finds a Java showroom, right, it will actually try to go there and brings only those documents, and then tries to calculate a n-gram overlap. Okay, n-gram overlap, and sees whichever document is matching, whichever the website is matching the most, it will actually try to show that as the first result. Second best, third best, based on the score, it will actually try to do that. So this is an example of rank retrieval model. Jaccard coefficient can be used to find out the best document, right? And there is TF-IDF model, and then the what you call it as Euclidean distance approach and cosine similarity. These are all different approaches to calculate rank of a document in a rank retrieval model. Okay, so in this, right, it will not look into term frequency, right? How many times a term is occurring, it will not look. How many times a term appears in the document, that thing is not given importance while doing Jaccard coefficient. Okay, it will actually try to take these are sets, right? When you look at Jaccard coefficient, it is set. So it will actually, if you have PRO twice, it will not POR twice, it will consider only once. If you have POR 100 times, it will consider only one. If you take words, right? If these are not charactergrams and you take words, if a particular word is occurring many times, even then it will take only once, because it is a set theory. It is based on set theory, right? So sometimes what happens is a most important document may get a less score because of not considering the number of occurrences of an important noun. Do you agree? Right, instead of getting that document as the first result, you may get it in the 10th page. Do you agree? Did you understand problem with Jaccard coefficient?
Yes, sir.
Right. So another problem is sometimes in a document, right, in a query, there is one term, and the same term may have occurred very rarely. The same thing, right? Opposite. Right? Too many times it is occurring, or very less times it is occurring. It will not be given importance. It is just that all these things will be given same importance, and based on other intersection over union score, right? The intersection over union may focus on other occurrences. Based on that, it may give score, and the most important document may fall on the 10th page because of that, right? So that is the problem with the Jaccard coefficient. To reduce or solve this problem, right, we need to give importance to moderately frequently occurring terms, and we should be giving importance to sometimes rare occurring terms also, right? In general, very frequently occurring words are not that important. Very rarely occurring terms are also not that important. Moderately occurring terms are more important. Okay, so this Jaccard coefficient is not considering that, because it is eliminating all the duplicates and trying to calculate the score. This weighted term frequency and weighted term TF-IDF, right? Term frequency and inverse document frequency approach will actually solve that problem. Okay, so how will it solve? Let me show you. Suppose that I calculated some score. Right? How we calculate this, I'll explain you later. But suppose that we actually calculated for word 1 in document 1 there is 0.3 score. Okay? For word 1, this is not probability. This is just a score. Okay, so I'll show you how we calculate this, and this is TF-IDF score. How we calculate and all that. First of all, we need to see how rank retrieval model works on a TF-IDF based matrix and a bag of words based matrix. That's what I'm trying to show. We have seen Jaccard coefficient and how it calculates the rank for each document based on a query. Now we need to see how TF-IDF matrix and bag of words matrix can be used to calculate rank. So I am taking TF-IDF matrix as an example, and then I will show you how to calculate rank. Okay. Suppose that word 1 and document 1, in document 1 has got 0.3 score. Word 5, document 1, 0.3.4. And word 6, document 1, 0.6. These scores are assigned based on a moderate occurrence of a word. If it is too many times occurring, you may get low score. If it is not occurring, you get 0 score. If it is occurring very rarely, also you will get less score. But if it is occurring moderately, then only you will get a high score. Right? There are formulas that will actually make this happen. Okay. So all these words in document 1, all these words in document 2, all these words in document 3, all these words in document 4. Right. So this is a document vector for these words. Okay. For these words, this is a document vector. So for all the documents, we'll take distinct words and then calculate the scores for them. For all the documents in the database, we take distinct words and calculate the scores, and we call that as a document vector. This part is clear, right? This is called as a document vector. We took all the distinct words and calculated scores, and we call that as a document vector. Okay. Now, suppose that somebody typed a query string, right? And in the query string, for that query string also, we will try to calculate a document vector for the words which are present in the database. Did you get this point? Right? Did you get what am I actually talking about? Initially, before we get the query, we have many documents in our database. We have taken those documents and found out all the distinct words from the documents. Okay. And calculated scores for each document for the word and called that vector as the document vector. Now a new query came in. Immediately what we need to do is we need to calculate document vector for the query. If you have to calculate document vector for the query, you will be able to calculate for for these words only. Why? I'll explain later. Okay. For those words I calculated document vector. Now what I'll do is I'll do a matrix multiplication of this vector with the vectors with the document vector or vector multiplication. The query document I'll take, first vector I'll take, do a vector multiplication. Second query document I take, multiply with the second document, calculate the score. Query document, third document, calculate score. Whichever document gives me the highest score, the multiplication, whichever gives me the highest score, I'll show that as the first document in the result. A little less score I'll show in the second result. Even less score I'll show in the third result. Here, while calculating TF-IDF scores, we considered the frequency also into, we actually took the frequency also into consideration. The results are going to be more appropriate compared to Jaccard coefficient based rank retrieval model. Okay. So the point here, how to calculate these numbers, we'll definitely cover. But the point you need to understand is how we are calculating score or how we are assigning rank to each document. This is the rank. Did you get it? How we are assigning rank to each document. The document 1 has got 0 rank with respect to this query. Document 2 has got 2.01 with respect to this query. Document 3 has got 0 score with respect to this query. If a new query comes in, right, there will be different scores assigned to these documents and the results will change, right? In Google, if you say how the kick movie is, you will get different results. I want to see a Java bike showroom near me. Different results will come because the rank is changing depending on the query. Got it? Got it? Any questions?
So rank for each document changes with respect to our input query and the words in this, right?
Yes, yes.
So we are giving rank to the documents, not to the words.
Yeah, rank to the document only. Ultimately, rank to the document. When you multiply this vector with this vector, you will get one number. When you multiply two vectors, you will get one number, right?
Yes.
You multiply with this vector, you get another number. This vector with this vector, you get another number. That number is the rank. However big the number, that is the biggest number. The ranked document is the first document. Second best, and third best, like that. Right?
Yeah. But there will be some cases where we are leaving some of the words in the query, right? Because let us take example here. We are taking
Yeah,
what
that's
one
a
the
good
words
point.
is.
That's a good point. That's a good point. Very good point, right? So what he's trying to say is, what you are trying to say is, right? I have a query where the none of the words are present in the database. What happens, right?
Yes.
Right. So I have a query, right? I have documents related to automobile industry. Okay. Now I have got a query. My database, right? I am a Google, right? I am Google. I have scraped all the documents related to automobile industry and created this matrix in the database. Okay, this matrix in the database. Now somebody came and trying to ask about healthcare domain, a query on healthcare domain, or you know trying to ask about a medicine, right? Is paracetamol works for fever, right? Paracetamol, fever, all those words are not going to be present in the database. Then you will get a zero scores for the query string. And when you multiply, right, none of the results will come. Is that right? Because we don't have, right? Got it?
Yes.
It is working, right? It is working for the purpose, but if you have to make the search engine work for all the strings, you should have that much data. That's where Google is successful.
And another thing is, once let's say there is not much matches found in this query string words also to be added to the dictionary of the big dictionary. They need to add. It's like a
Yes,
learning.
yes.
And next time, at least
This way,
when those words come in, we'll have 5 matches. Hello, sir. Hello, sir.
yeah. Can you hear me?
Yeah, still breaking, sir. For me, it's breaking. Your voice is breaking. I don't know about others.
For me also, it's
Is that the
breaking.
same thing?
Yeah.
Oh, from the beginning, is like that or now only?
No, now only, sir. Now it's
Now
audible.
only.
Sir. Now audible,
Yeah,
sir. Now.
this Beam internet is not that good. Maybe I have to change it to Reliance. Right? In our area, Reliance is not there. So I'm actually waiting for that. So this is another problem. We are having many technical problems. But yeah, but Girigar, your point is very right. Right? They're actually saving all the query strings, and the user, if somebody if Google showed some document as the first document, but most of the people are actually trying to click fourth one, they'll assign more rank, higher rank to the fourth one, because people are finding it more relevant, right? So this is all continuous learning, right? AML means continuous learning. Initial database they would have created like this, and then slowly they improved a lot. Google would have had many algorithms around. Let's look at the rank retrieval model or the search engine. Okay.
Sure, sir.
So I think we have got a decent clarity, right? So this is a TF-IDF matrix, but you can actually create a bag of words matrix. What is bag of words matrix? What is bag of words matrix?
Whether the word is present in the document or not.
How
For
many
each
times it
word.
is occurring? How many times, right? The count is the bag of words. It is not that 0, 1. It is actually bag of words will actually have count. But in the example I showed you, so count will take, okay. But what will happen if you take count as the, as the matrix? What problem you may get into is that there may be words which are like stop words. No, not only stop words, but in text, right, you will have words which are not important, that may have higher count, right? That may actually give more importance. If you have a big number here and this word 2 is not that important, and even in the query also that word is present, you will get highest score for the document 1. You will show that as the first document. So that's the problem with the bag of words representation. So we are going to go into a little more intelligent way of representing data, which is TF-IDF representation. So TF-IDF representation was found for rank retrieval model, not for classification models, but it is useful in classification models also. Okay, so we are going to understand the problems with bag of. So we have seen Jaccard coefficient and looked at problems. Now we'll see the term frequency matrix, we call it as. Okay, in I have actually, there is a typo here, right? In information retrieval, right? NLP, we call it as bag of words. Natural language processing, we call it as bag of words. In information retrieval concept, they call it as term frequency matrix. How many times a term occurred in the document? That is the term frequency matrix, right? And the other difference between information retrieval and NLP is that there we take words as columns, the terms as columns and documents as rows. Here we take terms as rows and documents as columns. We call this as a document vector, right? Term frequency document vector, right? Term frequency matrix it is, and this is called as term frequency document vector, right? So term frequency matrix, term document indices matrix will keep track of terms presence in the document, either 0 or 1, but term frequency matrix will keep track of number of times a word occurred in a document. Okay, this is bag of words only. Okay, in information retrieval we call it as term frequency matrix. Okay, and the note, number of occurrences in a document is not directly proportional to relevance of the document. Do you agree? What is our goal? We are trying to build a search engine, right? When you are doing a search engine, the query strings relevance is what is needed, right? When you actually take this kind of a representation and try to calculate rank by multiplying the query strings vector with the document vector, you may get score which is dependent on the number of occurrences of a term, right? That may not be appropriate. That may not be directly proportional, because stop words may occur many times, and if the document has got many stop words and the query string also has got many stop words, you may show wrong results as the best results in your search engine. Another example, a spam document may have the important word many times repeated. Only if I am trying to write artificial intelligence, I would have written very genuinely, and artificial intelligence word occurred only maybe twice or thrice in my document. But somebody wrote a document only with artificial intelligence 100 times. Right? If you take that, right, artificial intelligence, and you'll have 100 here, some query is there in that artificial intelligence is there, you will get high score and you will show that as the best document. So number of occurrences in document is not directly proportional to relevance of document. So that's a problem with bag of words retrieval model or the term frequency matrix based retrieval model. Most frequent words in all documents are not most important words. So this is the second point and first point are different. In a document, a word is occurring many times. That means the document is not important. Right? The second statement is a word is occurring in many documents. Right? Then the word is also may not be that important. most frequent words in all documents are not most important words. So two problems are there with bag of words representation or term frequency way of representation, and then trying to calculate rank based on it. What is the problem? Number of occurrences is not directly proportional in a document, right? In all the documents, a word is occurring many times, the word may not be important. Okay, word may be occurring many documents, the word may not be important. So these two are the problems, right? Stop words are the example here. Spam words, documents with spam documents with the same word occurring many times is this example. Got it? Do we agree? Yes, no?
Yes.
Yeah. So bag of words model will use term frequency matrix to understand patterns, right? So this is not important point. And the solution is the Tfidf scores, right? There are two scores we need to calculate: term frequency and inverse document frequency. Okay, let me try to explain what is term frequency and then inverse document frequency, and then we look into the other theory. So term frequency means how many times a term occurred in a document. Okay, term frequency means frequency of term T in a document D. In a particular document, how many times a term occurred. So term frequency will be there for each document. For a term, for each document, there is going to be a number. For T and D, there is going to be a number. So for T and D, there is a number. 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 Okay, that is term frequency. We said that number of occurrences in a document, right, of a term is not directly proportional to the relevance, right? So we can come up with a formula that actually tries to nullify this. It's a mathematical trick basically, right? Whatever the TF-IDF score is a mathematical trick to avoid the problem of giving more importance to most occurring term in a document. Okay, so how can we actually nullify that the most occurring thing? By applying log. Okay, that is called as weighted term frequency. Okay, normal term frequency is the just count. Weighted term frequency is the log applied term frequency is called as weighted term frequency. So the theory is like this. Sorry. If you take the number of occurrences, right? Number of occurrences of a term on y-axis, right? And right, documents on x-axis, right? Documents on x-axis, and then number of occurrences on y-axis. Then the importance may raise till some extent, and then it will actually become flat like that. Okay, even if you have maybe 10 words, till 10 words, it may be the importance on y-axis. Sorry, importance of words on y-axis and number of occurrences on x-axis, right? 10, 20, 30, 40. Right? The theory is like this, right? So beyond 10 occurrences, right? Beyond 20 occurrences, maybe the importance is not increasing exponentially. Till here it is increasing, but beyond that the importance is not increasing exponentially. So what we can do is, more than 10 you can actually nullify it, or more than 20 you can nullify it. If you apply log, right, log 10 base 10 is going to be 1, log 100 base 10 is going to be 2, right, log 1000 base 10 is going to be 3. So we are actually nullifying it. So the most the number of occurrences is not directly proportional to importance of the word. So we are actually doing that here. So, but if the word is occurring 0 times, right? Log 0 base 10 is undefined. So it's going to be 0. So undefined. So we are actually taking, if it is 0, right? We are taking 0, right? And then we are adding 1 here, because if the word is occurring only once, log 1 base 10 is equal to 0, right? 10 to the power of 0 and 0 log 10 base 10 is 1, so it's going to be 0. So to make it 1, right? So we added 1 plus log of whatever. Okay. So weighted term frequency is calculated like this to nullify the importance of word when it is occurring many times. Till some extent it is good. Beyond that it is not good. It is not needed. So nullify that, weighted term frequency is calculated. Okay. In Tfidf score calculation, the term frequency is weighted term frequency. The problem with bag of words model we are trying to solve by using this equation. One part of it. Any questions here? Okay, good. Right, that is term frequency part. Now I'll jump into the inverse document frequency. Okay. Once we understand this whole thing, right, I'll talk about this whole theory. This is for interview purposes. You need to understand, understand how exactly we are calculating TF-IDF score. So inverse document frequency can solve problem of giving more importance to most frequent words. Most frequent words in the sense, a word that is occurring in more documents. Okay. So if you take this here, the example, car occurred in 1000 documents. The document frequency is 1000. That means, see here, term frequency means in a document, a term is occurring how many times? In a document, term is occurring how many times? Document frequency means a word in how many documents it occurred. Right? The car occurred 1000 times and insurance occurred 100 times. The auto occurred 1 time. The best occurred 10,000 times. Okay. So here the inverse document frequency has given a more value to auto, a little more, less value to insurance, even less value to car, even less value to best. Okay. Why this is happening is, the, was, were, these kinds of stop words may occur in all the documents. If you have 1 million documents in your corpus, right? If you are calculating the inverse document frequency for a stop word, then log 10 base, what is n? The number of documents in the collection divided by document frequency. Each word may have occurred in all 1 million documents. Then what is this n by n? N by df? What is n? Number of documents, right? 1 million. df of is 1 million. Log 10, log 1 million divided by 1 million base 10 is going to be log 1, which is 0. Right? For a stop word, the inverse document frequency is given 0. Like that, a word is occurring many times, so you are actually giving less score. In many documents, right? In all the documents, you are giving less score. If the term is occurring in reality, in real time, even if you take an automobile industry based corpus and try to find out a vehicle word, vehicle, it may not occur in all the documents. In some documents, it may be mentioned as vehicle. In some documents, it may be mentioned as car. In some documents, it may be mentioned as four-wheeler, right? So in that case, right, for all those different words, there should be some score. But the stop word should get a less score, or these kinds of words, right, should get less score. That's the motto of calculating inverse document frequency. Ultimately, how will we calculate TF-IDF score? We multiply TF score, weighted term frequency score, with inverse document frequency score. See, this score we got by multiplying TF score with IDF score. Where is that? Did I show you somewhere? Yeah, see this here. So weighted, weighted term frequency into the inverse document frequency, right? This is the, I think I wrote some formula here, but don't be worried about that. I cannot highlight. So if Tf term frequency is greater than 0, right, we use this formula to calculate. If not, we actually put 0 there. Okay. Term frequency is not greater than 0, then anyway it is going to be 0, right? Tf is equal to 0 here, right? So if it's equal to 0, then it is going to be 0, right? So it's going to be 0, right? So 1 plus whatever the weighted term frequency into inverse document frequency. What this weighted term frequency is reducing the importance of most frequent word in a particular document, because for each document, for each word you need to calculate score. This word importance is calculated using TF score, and this word importance throughout all the documents is calculated by IDF score, and then you multiply both and you get an appropriate weightage for that particular word in a given document. If you use this kind of this TF IDF vector and then try to calculate rank, it is going to be more appropriate, because we try to eliminate the problem of giving more importance to most frequent words and giving importance to a word that is occurring more number of times in a given document. Got it? I'm going to talk about the same thing on Monday also. Right? Don't be worried even if you don't get it. But the gist of it you got, right? The TF IDF score and rank retrieval model and all.
Sir, just to avoid the stop words, so we are actually applying this IDF where it occurs more number of times, we are giving less score, or IDF score it becomes less. Yes, sir. Yeah. So let's say some word which is not a stop word, but it's really important and it occurred so many times. But we'll be punishing with less IDF score. So will it not impact? Sir?
Yes, it will. It will. So that's where you need to look at frequency distribution of words before you apply an algorithm. Whether bag of words applies well or TF IDF applies well, you need to analyze and do it.
Okay, sir.
But that detailed analysis we will not do, because generally random sampling works, right? If you take the corpus, huge corpus, right, the distribution is not going to be as you said most of the times, 99.99% of the times. Okay. That's where we may not do that much analysis, but if the corpus is small, we can do it and we should do it.
Okay.
Yeah, that's a good point, right? If I said, I said took an example of the automobile industry. If all documents have got the articles written as vehicle only, one person wrote the documents, right? The data set is like only one person wrote the whole data set. Then you should be careful using TF-IDF. Then you will get for the vehicle you will get 0 IDF score, and it will make 0 score, because you are multiplying TF score and IDF score and trying to calculate, right? So it will make score 0 in all the documents for that particular word, and that word is important. That will be present in the query, and you will get 0 score, or maybe less score for those, and the retrieval model will not work. So ultimately, I think by now you got it. AI is not doing anything. As a data scientist, we are actually doing more, right? We need to think a lot before we actually code, right?
Yes, sir.
Or while coding, you should think, you do experiment, you think you do experiment. So AI projects are not like, these web application development and, the mobile application development. You have a requirement, you have a tool that works, and you just take it and code it. And if some problem is there, you go search and fix it. No, every problem is a new thing on its own, and that's why they call it as data scientist. So you need to do research and iteratively improve it. So in the initial stages maybe I have shown, or on our website we have it, right? I'll show something. So the methodology, right? The methodology followed in AI. I don't know where I kept. So this is the methodology. CRISP-DM we call it as, or you take the data set, you do experimentation, you build a model, you see how much accuracy you understand. Again, you come back, you do like that. It is iterative because of the research component in it. And frankly speaking, on NLP, you cannot solve all the problems with AI. But industry is having an expectation on NLP that it can solve all the problems. It is not like human. It is not even like a 5-year-old kid in terms of NLP. Okay, there are many problems that cannot be solved using NLP. We'll see, right? By end of the course, right, you'll get how capable whether deep learning or NLP modules or whatever. Because we need to know the strengths and weaknesses. That's where we'll be able to propose a solution to the client and set the expectation so that we are not in trouble. We, in the sense, the company who got the project is not in trouble, right? So bottom line, we are doing all of it and we have tools. Okay, that's it for today.